So now that we know how to differentiate vectors, we'd like to apply these to a particular case, which is planar motion. So we assume we have a particle traveling along some curve within a plane, and we want to understand the velocities and accelerations of that particle. Okay, so we can think about, for example, if a car is going around an oval track, as it goes around a curve, it's got some velocity vector and acceleration vector associated with the curvature of the track and the speed of the car and all that sort of thing. We want to be able to understand all those kinematics using the stuff we've just learned. So what we want to do is think about some path along which the particle's traveling, and we're going to use a coordinate s to denote the arc length of that path. So the length of the over which we travel is denoted by this coordinate s. So our position vector is going to be written in terms of the coordinate s, which is a function of time, right? So as we travel along the path, s is always increasing. So s is arc length, and it's always increasing. Okay, so as delta s goes to 0, delta r over delta s goes to 1, and so delta r becomes tangent to the path. All right, so you can kind of see here there's our position vector here, and our position vector here. Slightly later, there's some vector that points from one tip to the next, and that's our delta r. That's the change in r over the time uh, t to t plus delta t over the arc s going to s plus delta s. Right? So as um, delta s goes to 0, then this delta r is going to approach the tangent to the circle. So if we have a position vector, the derivative of the position vector with respect to the arc length is a unit vector tangent to the path. Okay. We can also define kappa, which is the curvature, as the magnitude of that time of that spatial derivative. That is the derivative of the tangential unit vector with respect to the curvature. Okay. So the point here is that as the particle travels along this path, s is always increasing, but the tangent is changing, right? So the tangent here would be here. The tangent over here is here, and so the tangent is changing as we follow the path, as long as it's curved, right? So because the tangent is changing, then it has a derivative with respect to curvature, with respect to arc length. And that derivative of the tangent with respect to arc length is called the curvature. So the sharper this thing curves, the faster this changes and the higher the curvature. Okay. The dimensions here are 1 over length. And the unit normal, which is an inward normal perpendicular to the path, is 1 over the curvature times this derivative of u hat with respect to s. Okay. So we have two vectors of interest, a tangent vector and then a unit normal. All right. Um, there's something called an osculating plane defined by this tangent vector and this normal vector. Okay. The unit normal to the plane is the binormal unit vector. It's the cross product between these two, and it's perpendicular to the screen in this picture. And this so-called osculating circle is tangent to the path, and it has a radius that's the inverse of the curvature. So you can think of this radius of this circle as the radius of curvature of the path. That is, if you draw a circle around that, then rho will be the radius of that circle, and the circle has to be such that the curvatures match at the point of interest. So for example, if our path, it's a little hard to see, but if our path is this black curve here, Then down here, the curvature is such that drawing a circle to match the curvature at the bottom point gives a circle of this radius. Up here, the curvature is sharper, so we get a smaller circle here. Um, Out here, this is pretty straight. We need a huge circle to match the curvature there. Right here, we need a circle about this big. Okay. So this radius of curvature tells us how sharply that path S is changing. And in Cartesian coordinates, we can write it like this. You probably saw this in calculus years ago, and you've probably forgotten it. But the radius of curvature is 1 plus dy dx squared, all that to the 3/2 power, divided by the magnitude of the second derivative of y with respect to x. So the way this works is we have an xy plane here. We have a path marked um, denoted by some function y as a function of x. And so if we apply this formula, then we can get the curvature for any value of x. All right, so a particle traveling along this line has a tangential velocity, but the acceleration, as we'll find out, is both tangential and normal. All right. So if we deal first with velocity, the velocity is the time rate of change of the position vector. But if r is a function of s, then we can write this as dr ds ds dt. Okay. ds dt is just s dot. It's the time rate of change of the arc length. So it's the path, time rate of change of the path length essentially. And then the direction of the velocity is tangential, so it's this u hat t that we talked about before, and that's time dependent. And it's because that's time dependent, it's rotating, and so there's a rotational component to the derivative of that velocity vector, and that gives us this normal component of the acceleration, which we'll see in a minute. But for now, if we have some vector, r, which is a position vector, which is a function of s, then we can write the velocity of the particle as the magnitude of the velocity times the tangential unit vector, and the velocity is given by s dot. The speed is given by s dot. So it's the speed times the velocity times the unit vector tangential to the path. Now the acceleration is where it gets interesting. So now the acceleration is the time rate of change of the velocity. So it's v dot times u hat t plus v times u hat t dot. So v dot u hat t is straightforward. V u hat t is v times du hat t ds ds dt. Chain rule like before. ds dt is the velocity as we saw before. So that's going to give us a v squared term here. And then du hat ds is 1 over rho times un dot. So it's inwardly normal, and the magnitude is 1 over the radius of curvature. Okay, so the acceleration of our particle, which is traveling in the planar motion, is the time rate of change of the speed times the tangential unit vector plus v squared over rho times the normal unit vector, and it's inwardly normal. So if, for example, the velocity of our particle is constant, but it's moving in a curve, this term is 0, but you still have an acceleration due to the curvature. All right, and that's the key to this whole thing, is v squared over rho, inwardly normal, is the acceleration of a particle traveling at constant speed on a curve. And then it's the radius of curvature that says how big that velocity is. Right? So a couple of examples. Suppose we have an airplane flying in a loop. So we're looking from the side, and here's the airplane. It's flying along. All of a sudden, it does a loop-de-loop and then comes back. At the bottom of the loop, it's going 140 miles per hour, and the pilot feels 4 G's of acceleration. So what's the radius of the loop? Well, the acceleration is v dot times u hat t plus v squared over rho un hat. We're going to assume the velocity is constant, so this term goes to 0. So the acceleration, which is 4g, is v squared over rho. We're given v, we're given the acceleration, and we just solve for rho. Okay, so rho is v0 squared over 4g, and what you get for this is 327 feet. So if you're going at 140 miles an hour and you fly a loop which has a radius of 327 feet, then the acceleration felt by the pilot will be 4 Gs. It's pretty substantial. All right, one more. Suppose there's a truck that's on a highway and it's getting on an off ramp, and the off ramp is circular, so it's going to travel around this circle. It's moving at 55 miles an hour to start. The ramp is a circular arc with a radius of 150 feet, right? So the radius of curvature of this arc is 150 feet, and it's a circle. Then what's the constant rate of change of the truck's speed that will allow it to just stop at B? That is, having gone through 90 degrees of the circle. All right. So there's two ways to do this. One is we know what happens when we're traveling with constant acceleration. We saw this in a previous lecture where the square of the velocity at any time is the square of the initial velocity plus 2 times acceleration times the length traveled, s minus s naught. So if we set s naught to 0, s is the arc length of this quarter circle here, ac is acceleration that we're trying to calculate, and then v naught is 55 miles per hour, and the final velocity is 0. So we can just calculate AC. But we can also use what we just derived. So v dot is the acceleration, which is dv dt, which is dv ds, ds dt, which we can write as v dv ds. Okay? So AC ds is v dv. So we can just integrate both sides of that. AC is constant. We've been told that. So AC times s minus 0, where 0 is assumed to be the initial arc length, is just the integral here, 1/2 of 0 minus v0 squared. So the acceleration we need to pull this off is minus v0 squared over 2s, which is minus 13.8 feet. Okay. Remember, s is just 1/2 pi times the radius of curvature, which is 235.6 feet. Okay, so that gives us the acceleration we need to stop just through 90 degrees of that arc. And so the acceleration is negative, which is good because we're decelerating, and it's minus 13.8 feet per second squared. Okay, let's do one more example. Okay, so we have a trebuchet, and it's flinging a pumpkin. Right, so we have a coordinate system xy with the origin at just the release point of the pumpkin, and the pumpkin's released with an initial velocity v naught. And what we want to know is the time rate of change of the speed just when we release the pumpkin, and then the radius of curvature of the pumpkin's trajectory at the highest point. So what's the time rate of change of the speed just as we release, and then at the highest point up here, what's the radius of curvature? So the velocity is always tangent to the path, we know that, and the tangent at the origin is at an angle beta from the axis. So we assume the launch angle is beta, and we have a velocity vector here. The magnitude is v naught. The tangent vector is u hat sub t. And there's a normal vector u hat sub n, which is in this direction here. Okay, so the time rate of change of the speed is v dot, which is acceleration tangential to the path of the pumpkin, and it's just minus g sine of beta, right? So essentially, it's the tangential component of the acceleration. There's no acceleration horizontally. There's only acceleration vertically, and so the tangential component is the initial time rate of change of the speed. All right. At the highest point, the acceleration, the tangential acceleration is 0 because the tangential acceleration is horizontal and there's no horizontal acceleration. And the normal acceleration is g, right? Because the normal acceleration is this way, and the acceleration is the acceleration due to gravity. So the horizontal velocity is just v naught cosine beta. And because we have the normal acceleration is v squared over rho, then it's VH squared over AHN, right? The vertical velocity right at the peak is zero, right? So the speed is just v squared vh squared, right? Which is v naught cosine beta. So it's v naught squared cosine squared beta divided by the acceleration, which is g, and that gives us the radius of curvature. And so if you could crunch through the numbers, then you'd have that. All right, so that's basically planar motion. The main thing is you've got both tangential and normal components of acceleration, and you have to keep that in mind as you go through these problems.